how do we know if our experiences are real? It's an age-old philosophical question that's been explored in movies like The Matrix and The 13th Floor. Imagine you're connected to an advanced supercomputer, one that sends signals to your brain to make you think you're living your regular life. But all the while, you're actually sitting in a lab connected to a computer. And it's so realistic, so identical to the real world, that you can't tell the difference between the simulation and your own real-life experiences. The question is, in this moment, how would you know if you're in a simulation or not, or if any of your experiences were really happening? This idea is known as the simulation hypothesis, and Elon Musk thinks it's not only possible, but that it's very likely that we're living in a simulation. And his logic goes like this. First of all, the universe is 13.8 billion years old, but human civilization, as we know it, is only about 10,000 years old. Secondly, 40 years ago, we had video games like Pong, which was basically two moving rectangles and a dot. But today, we have immersive photorealistic 3D graphics with millions of people playing, all at the same time, and it's only getting better every year. Third, if we assume any rate of improvement at all, even a 1% improvement per year, we should reach a point where we can't tell the difference between these simulations and reality. It might happen 100 years from now. It might happen 1,000 years from now. But either way, it's almost certain that on a long enough timeline, we will eventually reach that point. Unless something stops us from getting there, like an extinction level event. Fourth, if we ever did gain the technology to build a simulation, then we'd be able to build many, many simulations. And so if you accept these 4 points, then right now we're living in one of two possible timelines. In the first timeline, we're living in the actual world, or what Elon Musk would call base reality. In this scenario, we're living in a timeline where we haven't built a simulation yet, and as our technology continues to get better, if we don't build a simulation, then it has to be because something very bad happens that stops us from getting there. Like environmental damage, or a nuclear conflict, for example. The second possible timeline is that we will eventually build a simulation, and if we do build one, there's no reason why we wouldn't be able to build more than one simulation, maybe even hundreds or millions of them, which means that there would be a much higher number of simulated realities than non-simulated ones. The thing is, right now, from our current perspective, it's impossible to tell which of these two timelines we're actually living in. It feels like we're living in the 2020s, but we could just as easily be in the year 35,000, plugged into a computer so advanced that it can recreate all of the experiences we see and feel all around us. And because there's only one base reality, the odds that we're living in one of the millions of possible simulated worlds is much higher than the odds that we're living in the real world. Whether or not you agree, Elon Musk isn't alone here. A lot of smart people believe that the simulation hypothesis is true. Take, for example, computer scientist Rizwan Virk. He says that he once played a virtual reality game that was so realistic and so immersive that he forgot that he was even playing a game at all, and that he was really just sitting in an empty room with a headset on. Virk's work aims to show that the simulation hypothesis helps explain many of the mysteries we find in physics, and it explains it in a way that's better than what we'd expect if we were living in base reality. One example comes from an area of physics called quantum theory. If we could zoom into your body, we'd find that you're made up of tiny atoms, about 7 octillion of them. That's another way of saying 7 billion billion billion. And if you could look at one of those atoms, you'd find a nucleus, which is made of protons and neutrons. And floating around it, you'd find tiny particles called electrons. When we're looking at things at such a tiny level, science shows that they behave in very strange and unexpected ways. According to quantum theory, we can't know where a particle is until we measure it. But it's not because our measurements aren't accurate enough. It's because these tiny particles are actually in all the positions they could possibly be in, all at the same time. And it's not until we measure it that it collapses into one position. In quantum physics, this is called superposition. To see just how strange this is, physicist Erwin Schrödinger came up with a thought experiment that would become known as Schrödinger's cat. In this thought experiment, imagine that you're taking a cat and putting it in a sealed box with a device that has a 50% chance of killing it within the next hour. At the end of the hour, our common sense tells us that the cat is either dead or alive. It has to be one or the other. But according to quantum mechanics, in the moment just before you open the box, the cat is both alive and dead at the same time. And it's only when we open the box and observe what's happened that we can see if it's alive. In other words, whether or not the cat is dead or alive depends on an observer, which seems incredibly strange. But when physicists look at very tiny objects at the subatomic level, that's exactly what's happening. These particles are in two states, both at the same time. So how do we make sense of this? If we think about the universe as a computer simulation, then this actually makes a lot of sense. Let me explain. Imagine a piece of video. When we look at this jogger, it looks like he's made of skin, muscle, and tissue. But when we zoom in, we see that it's really just an image made up of smaller pixels. And each pixel is controlled by a program that switches on a certain amount of color and brightness to make the illusion that what we're seeing is real. And if we think about designing a video game world, it would take an impossibly huge amount of computer power to play all the pixels in that game, all at the same time. In order to deal with this problem, programmers have ways of optimizing computer resources by using certain rules. One of these rules is that they don't play every pixel at the same time. They only play those pixels that are being observed in the moment. In other words, in order to save computer power, a simulation only has to play the parts that you're actually watching in real time, which means that in a simulation where you see a car, there might be all sorts of things happening underneath the hood, but there's no need to actually play the pixels showing what's underneath the hood until an observer opens it. Rizwan Virk argues that this is exactly what's going on with the Schrödinger cat experiment. Theoretically, the cat is both dead and alive at the same time because our simulation hasn't rendered it yet. And it does this because if we're in a simulation, then it has to optimize its resources, because it would take such an incredibly huge amount of processing power to play every atom and molecule in the universe all at the same time within a simulation. But it doesn't end there. The simulation hypothesis also finds support in the work of scientist Max Tegmark from MIT, who also sees similarities between our world and the computer world. Imagine for a moment that you're a character in a video game, which is so advanced that you can't tell it apart from the real world. Tegmark says that once you begin exploring this video game world, it would feel to you like it was made of real, solid things. And yet, if you really studied what was happening in the video game environment and the equations by which things move, you'd eventually find that everything in that world is mathematical. And that's because the laws of physics in a video game are just mathematical rules created by a programmer. But Tegmark takes this argument one step further. He says that even if we're not living in a simulation, this same reasoning is true of our world, because the closer we look at things that seem non-mathematical, the more clear it becomes that they too can be understood with numbers. Here's how we can see this. Scientists have found all sorts of numbers that are consistent throughout our universe. For example, the speed of light is a universal constant that has an exact value of 299,792,458 meters per second. There's also the Planck constant h and the gravitational constant g, which is also consistent throughout the universe. And the fact that numbers seem to correspond so well with our reality suggests that there's a fundamental mathematical order within the structure of nature. Tegmark says that numbers match up so well to reality because numbers are ultimately the only thing that exists. In other words, math is our physical reality. This might sound like a revolutionary idea, but it's actually very old. In fact, it goes all the way back to ancient Greece, to a man many consider to be the father of Western numerology, Pythagoras. And one of his most famous statements was that everything is number. Pythagoras believed that every object in the universe follows a basic mathematical order, and each carries with it its own unique vibration, an idea he called musica universalis. You might think that if we live in a world of pure number, then that means we must be living in a cold and meaningless universe. But Pythagoras didn't think so. Interestingly, he proposed another foundational idea, the transmigration of souls. According to this idea, every soul is immortal, and when a person dies, the soul survives, and it goes into a new body. And each time our soul comes back to Earth in a new physical form, it's because we're supposed to learn new lessons. And it's only when we've absorbed all the lessons from the physical plane of existence that we can then move on to the higher plane of existence. But you might ask, how does the idea of souls fit in with the simulation hypothesis? Scientist Sylvester James Gates Jr. says that if we're living in a simulation, then you also have to accept the existence of ghosts or a soul. Why? Because if we're in a simulation, then there must be some kind of a substructure that we don't have access to that runs everything we see around us as an app. And if that's true, then when we die, what does that mean? It must mean that the underlying app that runs us still exists within that substructure. And as long as there's no damage to the underlying code or hardware, whoever is running the simulation can re-enable the app to bring you, or anyone we like, back into the world. If this is true, then isn't it possible that ancient ideas like reincarnation could also be explained by the simulation hypothesis? All of this seems to imply that if we are in a simulation, then there must exist something like an eternal soul. Although Gates is skeptical that we actually are in a simulation, he does admit that the concept of a soul is built into the simulation hypothesis. But this really just raises more questions than it answers. What does it mean to be a soul? If we reach the point where we can map out the human mind and upload it into a simulation, what would that mean? And if we are in a simulation, then who or what is running it? And why? Whether or not we're living in a simulation, what seems clear is that not only is the universe mathematical in nature, but it's very likely that we're all eternal souls. Many thinkers are now coming around to the idea that the soul really is a kind of pure energy and vibration. And whether or not you believe we're living in a simulation, it's beginning to look more and more like this vibration can be understood mathematically, with numbers. Virtually every religion in the world has some concept of the soul. Could it be that our ancestors were trying to speak ideas that could only find expression today, with our technology and scientific understanding? Or are we just using modern language to describe something our ancestors knew all along? What this reveals is that even today, with all our advances, in many ways we've come full circle, and we've returned to these ancient ideas, which have their origins in a system of divination that's more than 2,500 years old. And what it shows is that the principles of numerology are just as relevant today as they've ever been. So what do you think about the simulation hypothesis? Let me know in the comments. That's it for this video. If you enjoyed it and you'd like to see more content like this, please like and subscribe. It really does help me out with the YouTube algorithm. As always, thanks for watching, and I'll see you in the next video.